method signatures with LIGO and Virgo.
Thank you, Vanessa, for giving me this opportunity to talk with you. So the plan of this talk is to talk about something that is probably strictly related to what you do in this institute, which is the search for continuous gravitational waves, which is the prototypical, let's say, source that emits this kind of signal are neutron stars. So it's somehow related to what you do in this institute. Then, if I have time, I would like to cover also the part of that matter searches, which, spoiler, are done exactly with the same data analysis method we use for the classical continuous gravitational wave analysis. Okay, so just a brief introduction. All of you, I think, heard about the so-called compact binary coalescent gravitational wave events. These are the typical gravitational wave events we have detected so far, and the only one. Where in terms of energetics, we typically use this H0, which is the strain, saying how much energy has been released and how much energy has actually been captured by the interferometers. And for these systems, which are the most energetic ones, we arrive to values up to 10 to the minus 21. These are also in the family of transient signals because these last up to minutes if we are lucky. And typically the search, let me say, is more easier than the rest of the sources I will show you later, because the model, the waveform is somehow modeled, even if you can tell me no, but it's not true because you can, assume many much more models. But let's say it's easier among the four of them. Then we have the bursts. Bursts are typically gravitational wave signals emitted when there is a supernova explosion. And in terms of energetic, these are comparable with the compact binary coalescence events, even if we didn't really see any of these yet. It's still in the family of transients, so these are not long-lasting signals. But the difficulty here is that it's unmodelable, so we don't really can apply the easy matches filter in our data. Then we have the even more difficult search, in my opinion, which is the search for the so-called stochastic gravitational wave background. In terms of energetic, it's way lower than the two examples I showed you before. And okay, these can have different origins. It can be astrophysical, so you can imagine all the gravitational waves summed up together in an incoherent stochastic way, or also from cosmology. Okay. And then finally, we will focus on the main topic of this talk, which are continuous waves. I told you the prototypical example is a spinning neutron star with some degree of deformation. In terms of energetic, we are higher than the stochastic background, at least according to estimates, but we are way lower than in particular, the compact binary coalescent event. These two have in common the fact that these are long-lived signals, which can last, in general, longer than the observational run. The best thing of this is that somehow we can model the waveform, as I will try to explain later. Okay, so what is a continuous wave? We need to have some kind of nearly periodic mass soluble moment variation to have this kind of emission. Is long-lived, as I told you before, and so spinning neutron star with a degree of symmetry, or also a neutron star in an accreting system, sucking matter from a companion in an asymmetric way, of course. But recently, there has been a new branch of investigations using the same data analysis method, which point to more, let me call it, or exotic or extreme events. In particular, boson clouds, form of dark matter, for example, actions, which can clamp around spinning black hole. I hope I will have time to discuss about this. Or even very recently, we started to look for newborn neutron star signals, for example, post-merger remnants or magnetons as well. So these are, new things. You can find some information about the reasons. Well, okay, this is about. You can check this paper for the physics, let's say, and then you have these two about the latest results. Okay, so in terms of emission models for the standard neutron star case, we need to have a star which is somehow deviated from his symmetry. In the easy case, the standard model, the easy triaxial rotor spinning about one of the principal axes, we expect to have a gravitational wave emission of twice the spinning frequency, okay, of our star. In this case, we are not considering precession. And if we consider precession, this emission is no longer monochromatic. It can be dual harmonic, it can be more complex, where you can have multiple harmonics as well. So typically, we do not consider this precession. Then you have other occasions where you have dual harmonic emission. In particular, this is a particular configuration when you have a thinner superfluid to the crust, and then you basically have a dual harmonic emission at once and twice the spinning frequency of your star. So we started to look also for this type of signals. And then you have the classic air mode emission, which this is not exactly an equation, because if you consider all the non-relativistic effects and the equation of phase effects, this relation is not strict. So there are some searches which actually relax this assumption about the proportionality between the spin frequency and the gravitational wave frequency expected. And okay, you can think about many more models. You can check this Jones 2021 article for more. Okay, I told you this number before about the strain, the energetics, but why it's difficult to look for these signals? You can tell me, okay, you're looking for a theme, so basically it's not true, because basically we have many parameters entering in the game for which we have many uncertainties. First of all, the moment of inertia of the star, you can tell me what it is. The distance of the source, which can be inferred, but again, it's some uncertainty. Okay, the frequency of the gravitational wave, you measure that basically. And then you have this small little thing called ellipticity, which is basically the less constrained one, because this parameter here is connected to the equation of state of your star, and is somehow connected to how much the star can deviate from its symmetry. So you can probably tell me, even you are more expert than me, can tell me, well, this is not so easy to do. In particular, for the, let's say, the two main scenarios where you have these ellipticities, this deviation from the symmetry, is when you have crustal strain defects or magnetic fields that can sustain this ellipticity. And these numbers here have only upper limits, let's say, and are not really well constrained at all, unless you tell me it's not wrong, because that's what we know so far. Okay, so some numbers according to, so this little thing I told you is strongly related to what we put inside the neutron star. There are only upper estimates, at least theoretical models say that. The only real, let's say, value we have, which is not an upper limit, is this in this work of Brown, Woham et al., for which we expect to have fiducial ellipticities of 10⁻⁹ when we have a varied magnetic field of 10⁻⁴ Gauss, but this is a particular case, and in particular for milliseconds. We have many estimates of this, but really we cannot touch it. Okay. Then another question also for you: are more exotic objects can sustain bigger ellipticity? Why? How can it trigger? Can it generate gravitational wave in this? In the same way we are modeling it? These are really open questions. Okay, then again, let's go back to how we look for this signal. You tell me again, you're looking for a monochromatic signal, so a sinusoid is really easy, no? You go to the spectrum and that's it. That's not true, because what we actually look for is something like more similar to this, because you have, first of all, your detector is on Earth, the Earth is moving, and there are many other effects I will show you later. And this is not only, it's not the only difficulty. The difficulty is this. We're looking for this. So this is the data, the real data, and this is our signal. So, okay, fair enough. Okay, but there are some methods which can be used to extract this little signal from the noise. This is on scale, of course. These are 10 to the minus 20. Okay. So I told you the signal is not really monochromatic. Why? Because we have the source is spinning, is losing energy, and you can somehow represent the evolution of the frequency using a power law. This power law here depends on how the release of energy happens. It can happen via electromagnetic emission, purely gravitational emission, or Armo. So, yeah, also another extra parameter. Then we have the Doppler effect, of course, because our interferometer are on Earth. But we need to take into account this. So this is easy to be taken into account. We know V, which is the velocity of Earth. So we can take into account. And then you have many more variations, which can be, for example, wandering, glitching pulses, glitching pulses. And then even if you remove all these frequency modulation, you still have this sidereal variation of the amplitude, which basically tells you that you are not looking for a monochromatic, like a single peak here, but you are looking for 5 peaks. Because this sidereal variation, what does is to split your signal into 5 peaks. This could be good, actually, because you can say, okay, but then you can check for this pattern in your spectrum rather than just looking for a peak, which can be easily be mistaken with a line, with a noise. Indeed, this is what we do. But in general, there are many ways you can look for these signals. Of course, you have to make a choice between the computational cost. If you have limited resources, you cannot really, use much as filter all over your parameter space because your laptop will explode probably, and you cannot do on your laptop at all. So, what you can do on your laptop are the so-called targeted searches, which are less computationally expensive and are even the most sensitive ones. But okay, there is a let's say a trick here because you have to know all the parameters of your pulsar. In this case, you apply this method when you have known pulsar. Okay, you know everything, you know all the rotational parameters of your source, the sky position, and so on and so forth. This is the easy case where you apply matched filter. This is a subfamily of these searches where you basically relax a little bit your constraint. You remember the proportionality between the spin frequency of the star and the gravitational wave frequency. You can relax it a little bit. Then you have directed searches for which you basically assume as known only the sky position, and you can do it, for example, for supernova remnants, or for when you want to look for something specific in the sky, the Galactic Center, which can be a good place to look for these kind of signals. And then basically you have the blind or sky searches, which are the all sky surveys, for which you don't really assume anything as known. And these also are, of course, the most computationally expensive. And there are some between families of these methods. Okay, let's jump to the results. What's the time? Okay, so let's go to the results. I will just show you some examples of the searches I've mentioned you. Basically, those have been involved the most. These are the results for the supernova remnant search targeting 15 supernova remnants have been investigated. We use 3 complementary pipelines. We use the first 6 months of all 3 LIGO and Virgo data. As you can see here, we have been able to go below what we call the indirect H0 age limit, which basically tells you if my system is emitting all this energy in gravitational waves, you will expect to have a strain of this, which is an upper limit, of course. This is this line here. So basically what I tell you here is that we are going well below what we expect to have if the emission happens to be, let's say, 100% in gravitational waves. So this means that those systems are not emitting fully gravitational waves. So there is some other mechanism happening. The best results is 7.7 10 to minus 26. You remember before I told you the 10 to minus 27. So we are close, but not enough. It can be even lower. I mean, nobody knows it. We have many, so 15 of these targets. One show here is Bella Junior. Then we have also the results for Cassiopeia, CSIC, and many more. Okay. What can we say with this H0? So you stop your search there. No, you can try to say something more about the emission model, the emission mechanism I told you before. So if we translate this H0 we get in terms of the electricity, this is the formula here, you can have those plots here. So these are some examples. This is Galactic, for example, here. You see that we are going up to as low as 10⁻⁷. But if you remember before, I told you that Graham et al. Just gave us a number which is 10⁻⁹. So these curves are getting lower and lower as much the pipelines get more sensitive, and also especially the detectors. But we cannot say if we are touching the ground or not, because we only have upper estimates. Same situation for the R mode alpha amplitude. You can translate again, same game. No, you have H0. You can translate in terms of the R mode amplitude alpha. You can plot this curve here. Number says, okay, according to Johnson McDaniels, we should have electricity which are lower than 10⁻⁶. R mode amplitudes, according to Bondaresco et al., we should have R mode amplitudes that can be lower than 10⁻�3, at least theoretically, and then we go lower, but still we don't see anything. Okay. Fine. Another example is the Galactic Center search. Okay, this is the two searches I'm showing here are all directed searches, for which we only assume the sky position of known, and that's it. Indeed, we actually investigate a wide range of frequencies and also spin down. Okay, do you remember the formula I showed you before, the F dot? That F dot is the spin down. Okay, how the rate of energy loss. Okay, so we decided to do this search for isolated neutron star in the Galactic Center, because this is a very active and densely populated region, and because we know that many telescopes have detected a gigaelectron vortex lens. So there's something happening there. Okay, it can be, of course, a population of neutron stars. It can be also dark matter. Nobody knows. We need to find a way to try at least to test it. So we did this search using, again, this time the full LIGO and Virgo data. We point, let's say, to the sky coordinates of Sagittarius A star. We actually had one candidate left, which was not easy to rule out. So when I mean candidate of potential signal, we couldn't rule out completely using the standard methods of analysis. We had to develop a new method to dig into the detail of these candidates, but still we don't have enough significance for these candidates to say it's a real detection. So we are starting to have more and more difficulties in finding these starting the candidates, because before we started to have this bunch of candidates, it was easy to discover because the significance was very, very low. They didn't really show any pattern particular. The pattern I showed you before with the 5 vectors. So before it was easier. Now that we are going down in the sensitivity, it's more and more complicated to rule out candidates. It's probably the most expensive in terms of a human time-consuming part of the search, let me say. In this search, we reached also values comparable to the previous search, 7.6 times to the minus 26, even if this search reached a larger astrophysical range, okay, because we are using the full O3 data at this time. Again, we can have the same result for the electricity and the R mode amplitude here. We are more or less in the same situation before, but we can do something. We can change, for example, the moment of inertia, because I told you it's not, so we don't really know this number here. We can change the moment of inertia, and we see that if we use larger moments of inertia, our curve goes lower. So here again, it is possible to have this kind of moments of inertia. You can tell me. Okay, same situation here, similar to what happened in the previous search. So we are there, but we still don't see anything, even if we are putting more stringent elements that what theoretical models do. Okay, so I will probably go fast for this part because I don't know if I have enough time. So we realized that many of the methods we use for standard continuous wave signals for neutron stars can be applied to more exotic scenarios. For example, boson clouds. I will try to talk about these two things here. We are working on this, so basically to try to detect the gravitational wave from the inspiral phase of primordial black holes. Why primordial? Because if we don't have such low masses, you will have a shear basically. So in this case, we can use the same techniques. Boson clouds. Okay, so how are these systems formed? So you have these dark matter particles, which are ultralight scalar bosons, which can come around your spinning black hole. You have a very fast spinning black hole. You can imagine you throw a small little balls to a bigger ball, which is spinning really, really fast. At a certain point, when they start hitting these balls, these fast spinning balls, it will extract angular momentum. So the black hole will start slowing down, and then you will have this clumping of actual condensation of boson fields around your black hole, and your cloud around your black hole will form in this more or less depicted this way. This process, the formation process of the cloud, is on a time scale of days. So, and what happens when after this we have this formation of the cloud, when the superradiance instability stops, when we have the breakdown of this relation, the cloud starts to evaporate. It evaporates because we have annihilation of the particles and via emitting gravitational wave. This radiation happens during years. So basically, if we have to bet, it's more likely that we are in the phase of the depletion rather than in the phase of the formation of the cloud. So what happens when this cloud dissipates is emit a gravitational wave with a frequency which is twice the field frequency, and depends, of course, of the mass of the black hole, the mass of the boson, and we have the amplitude decrease in time because the amplitude is related to the mass of the cloud. So the cloud reduces, and also the gravitational wave amplitude will be reduced. It's very nice this system because in terms of mathematical description, it can be described fully with the hydrogen atom model. We have energy levels as well. We have a fine structure constant as well. So in this case, it's very let's say elegant in my opinion. In terms of the signal model, we do expect to have a small spin-off because the cloud is reducing, and so basically this H0 depends on the total mass of the system. So if the mass reduces, you have a small spin-off in the frequency. We also assume some string wandering because maybe it can happen. And we are able to basically prove this region here. So 50 hertz of the detector correspond to this combination of boson of 10 to the minus 13 electron volts and black holes of 10 solar masses, and also this number here for higher frequency. Fine. Okay, so we did the search. We arrived again also here in terms of the strain, because here for this system we are still talking about gravitational waves, and we are in this region here. For this signal we don't really have many estimates because it's a new field, because it's exotic. We don't have observations, of course. But okay, this can be, of course, a minimal H0, or we can be very good. For this, I cannot say, cross-cut. Not so many, at least. But we can use that curve to constrain somehow what we don't see. Okay, so you say, okay, I haven't seen any gravitational wave as low as 10 to the minus 25 at that frequency. I can, since there is a dependence of this H0 to the mass of the boson and the mass of the black hole, you can plot these exclusion regions. Okay, so for instance, here for clouds formed 10 to the 8 years ago, we say that there is no signal emitted from this combination of black holes and boson, at least assuming a distance of 1 kiloparsec, and of course, black hole spin very fast spinning 0.9. If you change these two numbers, you will have a different constraint here. And again, if you change the age of your system, you will have wider exclusion regions. You can also say something about how far away you were able to see those signals. Again, this graph has been obtained by using simulations. So you have your curves, you start simulating your system, changing boson masses and distances, and you start counting how many signals you start to see for given combinations. And what you have is that you have this particular shape here because the amplitude of the gravitational waves basically is related to the boson mass. Up to here, let's say the proportionality goes as the boson mass, but when you jump to higher boson masses, your gravitational wave will be down more. So basically, the suppression of the system evaporates more faster. Okay, if you have higher boson masses, so that's why you see this particular shape here. What we have seen is that we are able to say that for sure, let's say for 95% confidence level, sure, that you don't see any young system, okay, 10 to minus 3 years in the galaxy, 10 to 2, let's say. Why you see that the younger systems are more constrained than lower ones, than the older ones, because then when the boson cloud is formed, it's more energetic because HD escapes as the time goes on. So you haven't seen strong signals. You are more or less sure you are ruling out very energetic systems, so young ones. Okay. Okay, fine. Then let's jump to another search. This is not gravitational waves, but using gravitational waves interferometers. Here we are looking at ultralight vector bosons directly interacting with the detector, basically fitting the mirrors and creating some a differential straight. Okay, this is probably a naive description of what's really going on, but you can imagine we have this wind of ultralight vector bosons, which are surrounded the Earth, and so the interferometers. These vector fields can couple directly to the materials of the interferometer. These produce a time-dependent force, okay, acting on the mirrors. Actually, there are two contributes to this differential strain. One is due to the fact that the vector field depends on the location, okay, on the position you are in the space. So there is a spatial gradient. So the vector field here is not the same as the vector field there. And this basically tells you that one mirror is moving in a different way than the other one. Then you have another effect, which is due to the fact that the light travels in a finite time. If you sum up the two contributes, you will have the total strain of this particular configuration. We are talking again same numbers, so more or less the problem would be then if we have somehow a detection, you cannot, or you have to find a way to distinguish with this and the previous searches I told you before. So, but okay, let's one problem at a time. What we did is apply two methods this way. In this way, these are even, let me say, from a point of view, the data analysis is even simpler than the case of the LIGO. So far enough. But again, even this, we succeed in putting some constraints on the coupling strength between the vector field and the mirrors. and the interferometers. Actually, we realized that these constraints are even more stringent than classical standard experiments aim to do this kind of aim to look for these particular signatures. You can tell me, okay, it's a very naive interpretation. You can be right, I mean, it's fine. But at least we tried for the first time to use interferometers to do different things, okay? And I think I'm concluding now. So, of course, we can talk about all the assumptions I made so far. But, okay, the spoiler is we didn't really have anything. We are trying to look for different sources, probably because we don't see anything yet. But who knows? So the real answer, I think, the real answer will be INO4, because if we don't really see anything in INO4, or there is something we are missing in the model, or really neutrons are very, very not asymmetric at all. But I don't really trust this claim. But if we really have some detection, especially if we have also an electromagnetic observation, this could be really, really nice in terms of interpreting what's going on inside the neuron. You can tell me again, you are wrong. No? Okay. We can talk about it here in the pizza. But yeah, I mean, we are like, I'm particularly, I mean, in this field, we have been working on this field since a long time. And I don't know, do I have to pursue this? No, why? You can tell me. Okay, hands up. Thank you very much.
The assumptions are both. Because I wouldn't expect you to find gravitational waves. Otherwise, the starting is down.
So now, basically, what has been done is, so you can find details in this one paper, but most of the time we don't really make many assumptions on this. The only assumptions we did is when we want to put constraints. So we don't really do searches for targeting. At least I'm not in this particular field. I'm not doing these kind of searches, but most of the searches are generic. Okay, so what you don't really do many assumptions on this. You can probably do, and would be probably more sensitive your search. But in general, we adapt what we have for the standard neutron star case or isolated with the some elasticity, also to the armor case, and you basically translate your results into constraints. So you don't really do a search for that armor.
I would expect if there is no emission, you will notice by the spinning down of the star.
Yeah. So yeah.
Easier than.
So you expect this basically. So if you have armor, you expect that your spin down will be fast. Your evolution, the evolution of the frequency would be different if you are purely. But this is so the problem is.
What I'm trying to say is that it would be easier to detect the down of the star rather than detecting a gravitational wave.
What do you mean by sorry?
That if there is gravitational emission,
yes,
that will be
yes, energy.
Moment of inertia, and you will notice that because the star is down,
yeah,
in an anomalous way.
Yes,
so you will notice that effect more easily than by detecting gravitational wave.
I think what you are thinking about they are not in the stability, right? Again, here what they are doing is that they are assuming that there is a saturation and it's equivalent to continuous wave. Not that you don't see the stability. It is not stability. For this set.
Yes,
okay,
for what
so
I showed them.
Exactly where you are looking to. I mean, where is it stability?
I think what there is, they are assuming, I don't know what I haven't seen that. I know when, but I don't know what they are. there is this instability doesn't go all the way down, all the way, but separates, and then it's like you have a continuous emission, rotational waves at the same way, basically, and then you can have this method.
Yes.
I think this is what they propose.
So you have the instability window, okay, and you focus on that window, and that's it. So when you have this maximum emission.
Then let's say that we will see that.
But I mean, how do you see it? Is it different, like, I mean, are you observing it in radio? Is that where you see that you see the signal?
Or anything.
Are you assuming that you have like actual, like separate information on the star from a different radio, like a radio observation, for example? Or like just from purely gravitational
Or
waves?
from the pictures.
Yeah, that's for not the search I show you, but for targeted search. So for there have been some other searches which there is one particular paper which is exactly for armored emission. But then you have to consider a different power law because you need to. So there is a combination of two terms here. It's more complicated than this if you want to do that particular. And it's not so. I try to give you the overall picture, but of course there are many things you need to consider.
It's related to this.
Mm-hmm.
Now, okay, this is ideally for the free, but in reality, no answer.
Yeah.
Especially if they are all the second, the n, and the errors make that the n can be in the thousand. So the question is how much the assumption on the value of n that describing the tiny solution, because I guess you are integrating over a long time, no?
Yes.
So how much this assumption affects the
So this is true for targeted searches, for which you do a full coherent search. Okay, if you miss that, you can miss the. But for semi-coherence, you basically take your data and you split your data into chunks. These chunks are no longer than 1 day, let's say. So probably you can recover this. In any case, let me say that this is theoretical, but in practice we use a Taylor series expansion to this. So our f is simply an f0 plus an f dot, which is a number fixed, and times the times. So if we have a detection, we can say something about the n. But otherwise, not so much.
Okay. Any more questions? Anyone online? Yes.
When you talk about this, one possibility is that the star is, could be bold, right? But another possibility are mountains, right?
Yes.
Is there any constraint to the size of the mountain?
I mean, typically, yes, you can convert this epsilon into centimeters. I cannot tell you the number, but if I remember correctly, it's less than a centimeter.
Yeah, but I don't know about some centimeters.
Less than a centimeter. Yeah.
I find out that potentially minus 6 and 10 pounds like some was that they are very, very extreme configuration, like
And I mean, those are usually target distances as well, because you might know it. Okay, and if there is no more questions, then let's thank Ornella again. And we're a bit early.
I just came for that.